Hi, welcome to the Signal Path. Today I'm going to do another product review for you guys. We're going to review the Rigol DSA1030A Spectrum Analyzer, which is the top-of-the-line spectrum analyzer that Rigol offers. You've seen this spectrum analyzer used in quite a few of my videos, and I've been using it for long enough that I feel comfortable doing a full review on it. And I've also gone through quite a few firmware revisions with Rigol to fix the little problems here and there, and I think that the firmware is now in a much better condition, and I'm very happy with it. So I want to go through showing you some of its capabilities, and we're going to do a whole bunch of experiments that show the limitations of the instrument, as well as the experiments themselves should also provide quite a few bit of learning experience. So I'm not just going to push the buttons and tell you what the functionalities are. I have devised a few experiments that I think you will enjoy. So let's take a look at the physical properties, just see what it looks like and what kind of how the buttons feel and how it looks physically, and then we will get into the experiments. So the Rigol DSA1030A comes with a protective front panel that displays the Rigol logo. It's a very nice protective panel, and I'm quite happy with this construction. It is very rigid, and it has reinforcing strips on the inside and a cutout for where the legs are. So if you plan to carry this around, because it does have a battery option, this would be very helpful to protect the screen. The screen itself is an 8.9-inch WGA, so it's an 800 by 400 pixel resolution. It's very nice and crisp and clear, and you've seen it in my other videos. It could be a little bit brighter, but other than that, I have no complaints, especially using it indoors. I don't see any problem. I haven't tried using it outdoor in the sun to see how it is. I don't have the battery option for this unit, and I don't think they do have that for North America. But otherwise, this screen is quite nice. The power button, just like all the other Rigol equipment, has the soft glow when it's in standby mode. USB in the front to get to maybe output some software into the spectrum analyzer, or to get images and data out, and a few other soft buttons to zoom into videos and in Windows and switch between windows and so on. A dedicated help button, which can be very useful if you're unfamiliar with some of the functionality. You can actually press that and then press the function, and you get the information, a complete help information on that particular function. The return button that brings you to the previous menu, a whole array of soft buttons on the right side. Doesn't have one on the left side, but a whole array on the right side with an up and the top and the bottom button which can advance you through the menus. The rest of the buttons are essentially the same on any spectrum analyzer. It's all the functions that provide you with typical spectrum analyzer access, like the frequency, the span, the amplitude. These three main buttons give you all the sweep control that you would want. Your bandwidth, your sweep parameters, and there's an auto tune button. I'll talk about that later. All kind of triggering functions are all available from the front. Also, your settings, that your detector and the demodulation settings also have dedicated buttons here that you can use. This particular model also has a series of advanced measurement functions that you can access with the measure button. So all the buttons that are gray have an LED behind them that light up, letting you know that they're active. So the source button, for example, here is related to the tracking generator. So if the source is on, you know that the tracking generator is producing power. There's of course other buttons, system utility and so on. A whole dedicated set of buttons for the marker, which is very useful. These are the buttons that you would be using the most if you're actually getting measurements from the unit, to find the peak and going to the left to the right peak and so on. There's of course a free rotating wheel which has probably an optical encoder in there, and it feels very nice. It has very distinct steps, so you know that you have gone to the next step, and a dedicated up and down button, which is the same as if you were to essentially make a one turn on this. So you can either use these or the soft rotation knob. There's a probe power on the front, which I think I've used in some of the other videos before. This is used to provide power to an active probe, and you can actually turn this probe power on and off via the menus internally to the instrument, which is nice. So it's not always on, so you can turn your active probe off if you're not using it. And there's of course the RF input, the 50 ohm RF input in the front, and all the instruments that pretty much operate up to 26.5 gigahertz typically have a type N connector, and so does this. So type N connectors are quite large, and the cables are quite large. So usually I just convert from type N to an SMA before I connect to my circuit, or maybe to a BNC. Either way, you have to stay in a 50 ohm environment, as the RF input is 50 ohm. Unfortunately, it doesn't come with a Type N to SMA adapter or a BNC adapter. You have to purchase that separately yourself. And since this model has a tracking generator, again has a Type N connector that has the 50 ohm generator output from the front. So it's all the buttons, it has just the right number of buttons. They haven't really crowded the front, and then of course they have a dedicated keypad with all the dedicated units on the right side. So it resembles an Agilent spectrum analyzer in terms of how they have arranged the buttons. So it's nice. If you're familiar with that, you're going to feel right at home using this instrument. The back of the unit has the big battery compartment, which I don't have the battery on this particular model, but it has an Ethernet port, a USB port, and a VGA output. So the Ethernet and the USB port are LXI compatible. So again, every instrument from Rigol has at least a USB or at least a USB and an Ethernet port, and some of the other ones have GPIB connectors as well, which you can send Skippy commands to and communicate with the instrument remotely. It has a little lock so you can lock it to your desk if it's in a public environment or a lab, and it has a trigger input and a 10 megahertz reference input and output. So it's a bidirectional port, so you can either set the spectrum analyzer to accept a 10 megahertz reference, or you can use the spectrum analyzer to provide a 10 megahertz reference to a different instrument that you're using. It has a hard on and off switch at the back, and if you leave it in the on position, then the front power button will just simply glow and letting you know that it's in standby. And of course it has a power and a fuse that is on the right side. You can pop out and replace the fuse if something goes wrong. The legs on this can actually snap out, and if you do that, then the instrument will sit on an angle. So if you don't have it elevated such that it's at the eye level and you're looking down at it, you don't want it to be standing vertically, you want it to be leaning back. So by doing that, the instrument will lean back and it'll be much easier to operate and see the screen. So it's nice that they have this, and they lock into place. This is a relatively heavy instrument, and I have had no problem with it falling over or even being unstable. It's basically sitting rock solid on the desk, so no problems there. So let's power the unit on and take a look and see how long it takes for it to boot. Here we go. So upon power on, it goes through decompressing the firmware that's inside and getting ready to power on. And it goes through a series of self-tests, and you can see it boots up really fast, so you can get to your measurement very quickly. Usually you have to let spectrum analyzers warm up a little bit so that the internal crystals and so on warm up. And right now you can see usually when you power it on, it does the self-calibration, which is written right there. It goes through a calibration process, which it does its own internal LO alignment and so on. So it goes through that at power on, and then it goes back to doing measurements. So this happens automatically in the background every once in a while. While it's doing that, your measurements are of course paused, but that's normal for any spectrum analyzer. So this particular model goes from 9 kilohertz to 3 gigahertz, and it has the lowest displayed average noise level of any of the spectrum analyzers that Rigol offers. Its DANL is at minus 148 dBm. That is with the preamplifier enabled. So it has a front-end preamplifier that you can enable or disable. If you're looking at a very small signal and your noise floor of your instrument is too strong and is completely hiding your signal, you can enable the preamplifier. That will lower your noise figure because it provides you extra gain in the front end, and that will bring your signal out of the noise floor. The disadvantage of that is that the preamplifier has a much more strict linearity constraint, so you can't put in a large signal when the preamplifier is enabled. So we'll take a look at it also. It also has the minus 88 dBc per hertz at a 10 kilohertz offset phase noise. Again, it's the best one that Rigol offers, and it has a 10 hertz minimum resolution bandwidth that you can set to. So the other models do not go as low as 10 hertz on the resolution bandwidth. And you need to go very low if you want to distinguish signals that are very close in frequency together. Otherwise they will all fall within the same resolution bandwidth bin and you could not distinguish them. So we'll take a look again at that as well. But for now, we can see it powers on. Hopefully have a good idea of the screen. It's very nice and the contrast is very good. And when it starts up, it goes from basically 0 to 3 kilohertz. So let's start doing some measurements. So as our first experiment, let's start with something really simple. This is a Mytek PLL that has its own built-in synthesizer essentially. So it has a VCO and a crystal oscillator inside and a PLL inside, and it generates a constant 600 megahertz tone at its output. So the reason I'm using this is because it's a precision source. It's supposed to be very, very close to 600 megahertz. And it's a high power source. It puts out a lot of power. And I can use this to do some basic experiments. How is the frequency reporting of the spectrum analyzer? Is it reporting the correct power? We can verify both the power and the frequency measurement of the spectrum analyzer using a power meter and a frequency counter afterwards. So this guy needs a, it says right here, the guy needs a 15 volt to operate. So I'm going to give it a constant 15 volt source. And I'm doing that by using the Rigol power supply that I have reviewed in one of my previous videos. So here it is. I have set it to 15 volts. It's right now the output is disabled. You can see 15 volts written right there. And I am connecting it with this cable right here, which I can power the synthesizer directly from it. And then we will connect the output to the spectrum analyzer. So here on the spectrum analyzer side, I am using a type N to SMA converter. This is an Agilent one, it's a very high quality connector, and using this green SMA cable. So it's all ready to do a measurement. So first, let's connect this up. Oh, I get a hold of it. Ground goes to ground, 15 volts to 15 volts, and the output of the synthesizer is going to connect directly to the spectrum analyzer. I'm not going to use a torque wrench to tighten this. It's tight enough, but whenever you're doing RF measurements, you have to use a torque wrench to do that. I'll show you a torque wrench in the next section. So it's all connected up, and before we power it on, since we know nothing about the source, it's always a good practice to set your spectrum analyzer to expect a high input power. You cannot put more than 30 dBm, otherwise you will damage the instrument. So you should always stay below that, but in order to protect it, just to make sure that we're not going to overload the instrument, let's set the amplitude to something large, let's say 20 dBm. Should be good enough. So now when you set this to 20 dBm, the attenuator automatically switches in. So now the front end has a 30 dB attenuator in the front to make sure that everything stays nice and linear. So I'm going to enable the power, like so, and there it is. We can see right away our tones right there. So by using the peak button, I'm going to press the peak button on the spectrum analyzer, and it gives me directly the dominant tone at the output. So you're not going to get a single tone, of course. You're going to get some of its harmonics. You can see the second harmonic is present, the third and the fourth and the fifth are also there. But the second harmonic is significantly lower than the first harmonic. Each division is 10 dB if each division is 10 dB, then you have maybe about 25 dB of difference to the second harmonic. So the first harmonic says 600 megahertz exactly, and a 14.57 dBm. Now it has a lot of zeros after 600. I'm not so sure about that, because when you're looking at the signal from so far away, you really can't count on it that many zeros on a spectrum analyzer. But anyhow, we can let that pass. Now we can look, if I want to look at the signal more carefully and see some of its properties near its fundamental frequency, and to get a better, more accurate measurement of the frequency, I have to zoom in further. So I'm going to go under frequency, and under frequency under center, I'm going to click that, and I'm going to enter 600 megahertz. So now my fundamental tone is in the middle of the screen, and I'm going to make my span very small so I can really look at the signal close to its fundamental tone. So let's make the span only 10 megahertz, like so. So now what you see is this is the noise of the instrument on the top, and then this is of course the main fundamental tone, but the resolution bandwidth is too large. So I'm going to make the resolution bandwidth now smaller. It's at 30 kilohertz. So let's go further down. Now it's at 1 kilohertz, and I'm going to press the peak search button again, so it can give me now the peak, much more accurate peak of the signal. So with the span of, I'm sorry, the span is 1 megahertz, not 10 megahertz. So I have a span of 1 megahertz here, and I have the peak. The power is the same, and it should be the same. So the fundamental tone does not change with the resolution bandwidth, and it shouldn't. So it's 14.5 dBm, and the frequency is 599.998333 megahertz. I can reduce the resolution bandwidth further, like so. It will take a lot longer to make a sweep, but it will give us a more accurate reading. So it's going through. I'm going to press the peak again. It's done one measurement. There it is. So we can take that as our frequency measurement, and we can take that as our power measurement, and we can also do a phase noise measurement. So phase noise represents the amount of power that is within a 1 Hertz band away from the fundamental tone at a certain offset frequency. So there's a lot of information in that statement. Essentially what it means is that if we had an ideal oscillator, an ideal synthesizer, it would have power at only exactly one frequency and nowhere else. But of course, every output of every real synthesizer or oscillator has some phase modulation on it, where the phase and the frequency of the signal that's coming out is constantly moving back and forth due to thermal effects and shot noise and all kind of other properties of semiconductor devices. So what you want to do is you want to limit how much power you observe outside the main fundamental tone that you're interested in. So right now the main fundamental tone in this circuit is 600 megahertz, and we want to have power nowhere else. But this slope that you see here, this curve that you see here, tells us that there is power away from the fundamental, but that power keeps getting less and less as you get further and further away from your fundamental tone, and that's also to be expected. Even the shape of this is modeled, is a 1 over f and 1 over f squared shape, where the power increases exponentially at some point by the linear and then the square line. It reaches your fundamental tone. So we know very well what this means, but in order to characterize and provide a reference performance for a particular oscillator, we want to be able to measure its phase noise. So I want to know, let's just say, let's take 100 kilohertz as our offset. I want to know what the phase noise is of this oscillator at a 100 kilohertz offset from the fundamental. So how do we do that with the spectrum analyzer? Well, the Rigol spectrum analyzer gives us a wide range of resolution bandwidths, and it has in its own internal phase noise is quite good. It's minus 88 dBc per hertz at a 10 kilohertz offset. So unless my oscillator is better than that, I'm going to be able to measure it using this particular instrument. So let's look at it at a 100 kilohertz offset, and let's see what we can do. Right now our resolution bandwidth is 300 kilohertz. I'm sorry, it's 300 hertz, and we have a certain number of points that's displayed here. Now I want to make sure that the number of points that's displayed here and the resolution bandwidth have some kind of a connection, so I can extract information in a 1 hertz bin. Otherwise I'm going to have to set the resolution bandwidth to 1 hertz, which is going to take forever, and anyhow this instrument doesn't go below 10 hertz anyway. So let's make a nice number. Let's set our resolution bandwidth to 1 kilohertz. So every bin of measurement is 1 kilohertz large. Now we want 1 hertz, but let's start with 1 kilohertz. Now I want to make sure that every point represented on the screen corresponds to a single bin. How do I do that? Well, I'm going to check to see how many points I have. If I click on trace, sorry, not on trace. If I click on sweep, I have the number of points that's displayed here, written here, 601 points. So let's change that to 1000 and press, oops, I'm changing the wrong thing. I'm sorry, escape. Number of points, set it to 1000, enter. So now it has 1000 points. Unfortunately, it doesn't really reflect that onto the screen. You can see that it doesn't change the way the screen is displayed. If you use an adjuvant spectrum analyzer, when you enter 1000 points, then you can see more points and they become brighter. But anyhow, nonetheless, it's internally doing 1000 points. So now I have 1000 points, and each point is on a 1 kilohertz resolution bandwidth. So now I can begin to do my phase noise measurement. So let's take a peak value. So this was our original measurement. The peak value power we have at 14.4 dBm. So let's do some averaging to clear up some of this variation that happens. And usually you have to do averaging when you do phase noise measurement. So let's go under trace, and you can see it can tell you, it asks you how many averages you want. It's set to 100 by default, which is very large. So let's say number of averages to be 16. Now it doesn't start averaging unless you tell it to. So then I'm going to have to go under trace type. I'm going to say start doing power averaging. So now it's starting to do some averaging for me. I'm going to press the peak again. So now this is doing a power average. So everything is now relatively every measurement now has to be done in a relative fashion. So now you can see the trace has been smoothed out quite a bit. I have my peak there. Now I'm going to click on my marker, and I'm going to do a delta marker so I can take the difference between 2 points. There's my delta marker, and it's asking me how far do you want your delta marker to be. I can either use the knob and turn and go back and forth, or I can enter the value that I want. Since I know I want to do at 100 kilohertz offset, I can just enter 100 kilohertz. So it's doing 100.1 kilohertz, so it snaps to a particular internal frequency grid. So again, don't really like that, but it's not a big deal. So it says the difference between here to here is minus 77 dB. Now that's not minus 77 dB C per hertz, because the bins are not 1 hertz. The bins here are 1000. So there is a 30 dB extra power that you're measuring because your bin is 1000 times larger. So in reality, your phase noise is minus 107.4 as opposed to minus 77, because there's a 30 dB difference. But the nice thing about the Rigol, one of the options of the Rigol Spectrum Analyzer is that it has some functionality for the markers built into it. So if you press the marker button, the marker function button, it can give you several functions. One of them is noise marker. So by pressing the noise marker, it will take into account the resolution bandwidth, the number of points, and then it will give you a correct readout on your relative frequency, relative power measurement. So there you go, I press that. It resets the average, it's not a problem, but you can see now it says minus 107.7 dB C per hertz, so it's doing the correct translation for you. So the phase noise of this particular synthesizer that I have is minus 108 dB C per hertz at 100 kilohertz offset, which matches its specification. Now the only other thing that I want to verify was the measured frequency and the measured power. I've written them down, so now we're going to compare them with what the instrument is reporting. So in order to verify the power, I'm going to use an Agilent power meter and an HP power sensor. Now, we have to be careful here, especially if you're doing high frequency measurements. So when I measure the power using the spectrum analyzer, I'm measuring the power at the edge of the type N connector of the instrument. So the loss of the cable and the loss of this connector are included in my measurement. Now when I'm going to measure the power, I'm going to have a different connector. Now at 600 megahertz it may not make much of a difference, but it will make difference in higher frequencies. So I'm going to disconnect this from the spectrum analyzer, and I've already calibrated my power sensor and I zeroed it, as you've seen in the previous video. So that's done. Now I'm going to use a different connector. I'm going to use this type N to SMA connector. So we can assume that the loss of this connector is comparable to the loss of the connector that used to be on the spectrum analyzer. So hopefully that's going to give us a relatively accurate measurement. So the spectrum analyzer reported a minus 14.4, minus 14.5 dB of power. So I'm going to connect this up like so. And everything is nice and tight. And we're going to look at the measured power. So the measured power here is reported at 13.72 dBm. So it's about just under 1 dB different from what the spectrum analyzer is reporting, which is within the specification of the spectrum analyzer, because the spectrum analyzer has about a dB of amplitude flatness. That's normal. All spectrum analyzers have that. That's why if you want to make a very precise power measurement, you have to use a power meter and a power sensor. But this is well within spec, so I have no problem with that. And now we can move on to measure the frequency. So I've moved to the other side of the lab, and here I have my HP frequency counter that goes all the way up to 18 gigahertz. So we're going to use that to measure the frequency of the synthesizer to see if it is close to or matches the frequency reported by the spectrum analyzer. Now, this particular frequency counter operates with very low input power, and it says that the maximum I should feed it is 7 dBm if I want to have a reliable measurement. So what I'm going to do is I'm going to add a 20 dB attenuator in front of this guy so that I can drop down the power coming from the synthesizer, the PLL, by 20 dB before feeding into this. So each of these guys are 10 dB attenuators. There's 2 of them in a row, and they work all the way up to 18 gigahertz, but of course we're only going to use them at 600. So I'm going to use the input 1, which is for the higher frequency inputs. I'm going to put the attenuator in there and connect the input signal. There you go, and we begin to see a measurement. Let's go closer. 599.99863, and the spectrum analyzer was reporting 599.997497. That was the last measurement that I read. So again, extremely close to what the frequency counter is reporting. So the frequency and the amplitude accuracy of the spectrum analyzer at this random 600 megahertz level that I chose is very good. So next I'd like to take a look at how the spectrum analyzer behaves at a very low frequency close to where it is rated. So you can notice that the spectrum analyzer is rated to only work from 9 kilohertz and up. So that's a shame, because at low frequency sometimes you're working in the audio ranges or you want to see a tone at 1 kilohertz. Now I want to know, can this spectrum analyzer still display it? Now the reason why it only works at 9 kilohertz is because there is a DC blocking cap inside the instrument that prevents any signals at lower frequencies to go through. So it has its own essentially high pass filter. Now the DC coupling cap that's inside has a lot of benefits. It allows you to put DC voltages at the input of the spectrum analyzer without damaging it. For example, this particular spectrum analyzer can take let me see, up to 50 volts of DC at its input without being damaged, and that's because above the 50 volt then you start to damage the capacitor that's inside. So let's see how it behaves below 9 kilohertz. Can we still use it at those frequency range? So let me preset. So now I've preset the instrument. You should always preset spectrum analyzer at the beginning of every new measurement. So we start at 0. Now let's stop the frequency at, let's say, 20 kilohertz. Like so. So you can see there's already, this is a DC measurement, so it's measuring its own internal DC voltage. So that's, again, you have to ignore that. And there's a sharp drop, and then you see the rest. So now let's check let's lower the frequency, the resolution bandwidth to, let's say, oh, sorry, too low. Let's say 100 hertz. There you go. So that's not so bad. So this is 100 hertz resolution bandwidth, and now let's do some simple measurements. Now, in order to do that, what I'm going to do is I'm going to use, since my my DG5000 series waveform generator is too far away, so I'm going to use the DG4162 here, which is, you know, for this type of measurement is not a problem. So I'm going to use channel 1. I have a BNC to SMA connector at the output, so I can connect my cable to. Then there's the other end. I'm going to connect the other end directly to the spectrum analyzer. These two instruments are close together. It makes it easy to do this. So let's go under utility, and let's go under channel 1 setup, and let's set the output resistance to be equal to 50 ohms, because the spectrum analyzer has a 50 ohm input. So by setting the channel resistance to 50 ohm, we are going to get correct measurement, correct readouts from the waveform generator. So we're done with that. Come out of this. So right now it's the output is turned off. So let's put a tone that is at within the range of the spectrum analyzer. So let's do 10 kilohertz. 10 kilohertz, no problem. And let's set the amplitude to be at, let's say, -3 dBm. -3, and dBm is an option. There we go. Perfect. So now I can enable the output by doing the following. There it is. So let's see what we're getting here. So this is supposed to be a tone at 10 kilohertz at 0 dBm. Let me do a peak search. Sorry, at -3 dBm. So I'm doing a peak search, and you can see it is at 10 kilohertz, and it is at -3.5 dBm, again within the amplitude uncertainty of the instrument. So it works no problem. So let me reduce the resolution bandwidth a little bit more. Set it to 30. Oh, it's going to be too slow. Never mind. Let's just have it at 100 hertz. No problem. And I can read everything as expected. So now what I want to do is, and if I go higher in frequency, let me do that. For example, I can go to 11, 12, and so on. This is 12. Again, the amplitude hasn't changed. Now, but if I try to push the frequency lower, so this is the edge. This is 9 kilohertz. This is where the instrument is rated at, and I'm still seeing the correct amplitude. Now I'm going to lower it even further. So now, as soon as I go to 8 kilohertz, now we are below the instrument rating. There we go. But look, we're still seeing. You can still do a measurement without any problems, except that, you know, the amplitude is dropping. I can go 6. Now this is at 6. You can see now it says -4.6. So now it's out of spec. But you can still see a tone, and I really like that, because if you just want to see if a tone is present and you don't have a spectrum analyzer, or if you have multiple tones and you're not sure and you want to see if they're there, this is a perfect way. You can still see it, but you will not be able to get a very accurate amplitude measurement, but the frequency measurement has no problem. So let me go to push it really to the extreme, and this is at 1 kilohertz. Now at 1 kilohertz it says minus 16 dBm, even though we are putting minus 3 dBm. So we have lost a significant amplitude because of the high pass behavior of the instrument, but you can still see your tone even at 1 kilohertz, and I'm very happy about that, because you can find something that you're looking for that's below 9 kilohertz. In order for me to easily see the frequency response of the spectrum analyzer at low frequencies, what I've done is that I've set the spectrum, the waveform generator to generate a sync function at a 500 hertz repetition with a 6 dBm of power. So now a sync function has a rectangular frequency response. So by creating a sync function in time, you're creating a frequency response that's broad and is supposed to be rectangular in shape. So by looking at the spectrum that we can measure, you can quickly get a nice idea of how the spectrum analyzer behaves at low frequencies. You can see very nice and flat response here. If I go onto the marker, I can move the marker around. You know, let's say I'm around, let's set the marker to 9 kilohertz. So you can see here that we're very nice and flat in this region, and then as we get to lower and lower frequencies, there is a low pass or rather a high pass behavior, and we are not able to detect the amplitude correctly anymore. But we are able to detect something, meaning that you can still use this guy at lower frequencies to detect the signal, but you cannot know exactly what the amplitude is. Or if you model this and you know exactly the loss of your instrument, you can compensate for that, and then you can get even an accurate reading. So very nice that you can still use it below 9 kilohertz. So let's look at the spectrum analyzer's capability of viewing very, very small amplitude signals. So here I've preset the instrument to its default setting, and it's showing a full span. So let's do this experiment at let's say 1.5 gigahertz. So I have the HP signal generator here that I repaired in one of the older videos, and since it's sitting on the desk, we can use this one, and it can also generate very low signal amplitude because it has a 120 dB attenuator built into it. So I've set it to 1500 megahertz right here, and right now it's set to minus 10 dBm, so I can go ahead and enable the signal. So now if I look at the spectrum analyzer, of course there's no problem, it's minus 10 dBm. It's very easy to detect a minus 10 dBm signal, and I can set the marker to detect the peak value, and it's telling me it's minus 10.48 dBm, which is perfectly fine considering the cable and just generally the amplitude and accuracy of the spectrum analyzer. So let's go ahead and reduce the signal continuously. So I'm going to go to the signal generator, and from minus 10 I'm going to continuously reduce it. So it's minus 20, 30, 40, and 50. So now we're beginning to reach the noise floor of the instrument. So there are several things we can do to still be able to recover the signal and be able to see it. So if I go to minus 60 dBm, now you basically almost cannot see it. So let's zoom in to the spectrum a little bit. So instead of going the whole span, let's look at it from let's say 1.4 gigahertz to 1.6 gigahertz. Stop at 1.6 gigahertz. So the signal should still be in the center of the screen. So let me reduce the resolution bandwidth of the instrument. So I'm going to go down in resolution bandwidth, and I am at the resolution bandwidth of 3 megahertz. I'd say 1 megahertz. It's now 300 kilohertz, 100 kilohertz, 30 kilohertz, and 10 kilohertz. So at 10 kilohertz resolution bandwidth at that span, you can now again see the signal, and it says minus 60.40 dBm, and now it says minus, somewhere around minus 60. So that's still pretty good. So we can go further. Now minus 70. Now it's a minus 80. So again, now it's below the noise floor. So this time, let's go to the amplitude and set the reference so that the reference doesn't start at 0 dBm, because the instrument automatically puts a 10 dB attenuator in the front of the instrument's input to protect itself for larger input signals and also to be linear. But since the signal is so small, we don't need a 10 dB attenuator. So let me change the reference level to be at minus 50 dBm and turn the attenuation off. Now as soon as I turn the attenuation to 0, because the attenuation is right in the front of the instrument, I will gain 10 dB of noise figure because it's right in the front of the RF input. So if I do that, I will get 10 dB of noise floor improvement. Makes sense. Now if I go to marker, again, now I see minus 80 dBm. So now we can again see our signal. So let's go even further. Minus 90. So again, we're at the noise floor. So let me reduce the span, because if I reduce the resolution bandwidth anymore, then the sweep speed will become too slow and you have to wait for a long time. Since we know the signal is around this area, I can afford to do that. So instead of starting from 1.4, let me start at 1.49 gigahertz, and let me stop at 1.51 gigahertz. So again, the span is, so you don't have to enter the, of course, the start and stop. This is just what I'm used to. You can enter the center and the span. So from now on we will do that. So I can reduce the resolution bandwidth even further. Now it's 10 kilohertz, now it's 3 kilohertz, now we're beginning to see the signal again. Now it's at 1 kilohertz. So let me change the span even smaller. Let's make the span 1 megahertz. There it is. Marker peak. Now we can see our signal again. And I can go ahead and further reduce the resolution bandwidth. 300 hertz. And now it's 100 hertz. Now at the 100 hertz resolution bandwidth, this is extremely slow. So let me reduce the span even further. So let's make the span, let's say 10 kilohertz. There it is. Now, because the span is so small, I actually lost the signal because the signal is not within the 10 kilohertz 10 kilohertz span that I have here. So I'm going to have to change the span back up again. Let me see if we can see the signal again. That way I can use one of the other functions to fix this problem. Okay, so here's our signal. So I can say marker, and I can say peak surge. Now I have other options that I can do. What I can do is I can click on this button. Oops. If I click on the marker button with the arrow on it, it gives me a whole bunch of functions I can perform on the marker. It can set the marker to be the center frequency, to be the step, to be the start, to do a stop. So because it's not perfectly in the center, if I click on marker to center frequency, it brings me to the center. Now I can go ahead and reduce my span even further. So I can go back down, 50 kilohertz, 20 kilohertz, 10 kilohertz, and I still have the signal perfectly in the middle. And even at 5 kilohertz. So I will do a peak again, and I will bring it to the center. Now I can reduce the resolution bandwidth even further, 30 and 10. So 10 is the lowest resolution bandwidth that this instrument supports. This is as low as you're going to be able to get your noise floor by just playing with the resolution bandwidth. And this 10 Hz resolution bandwidth option is very important for doing work like this, and the next experiment that I'm going to show, and only the DSA1030A supports this because it requires a very good internal PLL in order to be able to accomplish something like that. So I'm going to wait until I find the signal. There it is, and I'm going to bring it to the center, and I'm going to reduce the span even further. There it is. Here's our span of 1 kilohertz. And we should be able to see the signal, and there's our signal. So right now it's at minus 90, but you can see I still have quite a bit of dynamic range left. So let's go further down. Okay, so here's the signal peak. It's at minus 110 dBm, and if I go to, just to convince you that it is really a minus 110 dBm. So minus 110 dBm is a very, very, very small signal. So now, if I want to go even less than minus 110 dBm, I can no longer use the instrument's resolution bandwidth to do that because I'm already at the minimum resolution bandwidth. I cannot use the instrument's internal attenuator to do that because the input attenuator is already set to 0 dBm, so I cannot lower the noise figure anymore. So the only thing I can do is if I had an amplifier in the front of the instrument to further lower the noise figure. And in fact, the DSA1030A has a built-in preamplifier. So if we enable the built-in preamplifier, we will get even more improvement in the noise figure of the instrument to be able to take even smaller input signals. So let me set the input amplitude from minus 70 dBm since we're going very, very small. Let's set it to minus 80 dBm. There we go. So this just shifts the reference up. So here's our signal still at minus 110. And what I'm going to do is I'm going to enable, you can see right here, the RF preamplifier. So I can turn the RF preamplifier on, and you can have an eye on the noise floor of the instrument. There we go. I've turned it on, and we've gained another 20 dB or so in the noise floor. So you can see the noise floor went down, but the signal didn't. Of course not, because the signal is coming from outside. That's what we're measuring. The noise that you saw at the bottom is not from the synthesizer, but it's from the instrument itself. So now look at how much more dynamic range I have left and how much above the noise floor I still am. So the signal to noise ratio has significantly improved by doing that. So, but then you may ask, then why not always have the preamplifier on? Because if you set the preamplifier on, you limit what is the largest signal you can input to the instrument, and you seriously run into linearity when the preamp is on. So the preamp should only be on if you are measuring something very small. Not only do you run into the possibility of damaging the preamp if you put too much signal into it, you also become horribly non-linear and lose the performance of the instrument. So since we're measuring such a small signal, we can do that. So let's go even further down, minus 20. Minus 120 dBm. There you go, no problem. And minus 130 dBm. You're sweeping. And there it is. There's our signal. I can do a peak. I can put it in the center. That's it. That's pretty much as low as it goes. That is the smallest I can do. I can also reduce the video bandwidth. I think it can go even lower. There you go, 3 Hertz. I don't know how long it's going to take. There it is. And it doesn't really make much of a difference because you're limited at the noise floor at this point anyway. So you can see I can detect and it says minus 128.88 dBm. The instrument is set to minus 130. Let me see if I can go even lower. Minus 135. There it is, no problem. See, this is minus 136. At this point, you're, of course, the noise is comparable to the signal, so you're going to get some even more error than before. So I would say at 1.5 gigahertz, to reliably detect the signal, you can also still average this, and if you average it further, then some of the correlated noise goes further, so some of these peaks will even go away, and then you will get your signal back. But at this point, you're pretty much, you gain the signal and you lose it because of the noise. So minus 135 dBm at 1.5 gigahertz, by having the instrument set to its most sensitive operation, you can still detect the signals. That's pretty impressive, and it meets the spec. If I were to move the marker to here where the noise of the instrument is, the instrument is advertised to have a minus 148 average noise level, and it says minus 149, so it's good. It's exactly what they're saying. So let's do another experiment that actually showcases the importance of being able to detect small signals, not just in amplitude, but also signals that are close together in frequency. Now, in order to detect signals that are close together in frequency, you need a very good resolution bandwidth. And in order to detect small signals, you need a very good signal-to-noise ratio. So let's do an experiment for that. You've seen this board before. This is a Vertex 2 Pro FPGA development board that is capable of transmitting and receiving various types of data through all these SMA connectors that you see here. I've done some experiments with this before. So let's actually do something that researchers might or developers might need to do on a regular basis when they're testing a circuit that is either not working or they're not sure exactly what it's doing. So what I've done here is that I've configured the Vertex 2 FPGA to generate a PRBS random data sequence. It's a pseudo-random bit sequence. Now, PRBS sequences have some properties that make them very useful for data communication. PRBS sequences are periodic, so they keep repeating themselves, but they're also not quite random. Even though they behave very much like a random bit sequence, there is a generator function that can tell you exactly the bit sequence, and you can calculate the bit sequence very easily. Now, because of these properties, PRBS sequences are very useful for testing communication systems. So what I've done here is that I've set this FPGA to generate a PRBS random data sequence coming out of these ports. So the bottom 2 ports, these 2, are transmitters, and the top 2 are receivers. So every signal is differential. So it's a differential transmitter here and differential receiver here. So what I have done is that I've used one cable like this to connect one of the ports of the transmitter to one of the ports of the receiver. I have terminated the other port of the receiver, and I've taken the other port of the transmitter, the remaining differential one, I'm taking it directly to the Rigol Spectrum Analyzer. So by doing that, these pairs of transceivers are capable of operating in a single-ended mode. So even though only one of the differential signal is connected, they're still able to operate reliably without any errors. So I can look at the transmitter signal on the spectrum analyzer while simultaneously have established a loop for the FPGA to work on. So I'm not going to tell you the loop parameters. Let's try and and characterize them, let's look at the spectrum that's coming out of the FPGA right now. So here's the spectrum. There it is. So you've seen this spectrum before. I've shown it in a different other videos. So let me just preset the instrument so you know this is where we start with from scratch. Press escape to get rid of this. So you can see the very typical non-return to zero type signaling behavior. Now we only see from DC to 3 GHz. After this 3 GHz region, there's actually more side lobes because this resembles the frequency response of a rectangular pulse in the time domain, because the rectangular pulse in the time domain is what our signal shaping, the NRZ, actually looks like. So this will go down like this, and then we'll have lobes after which we cannot see. Now, if we could see the first lobe, where the first lobe begins, we could actually tell what the data rate is. Now we can see this has gone all the way down already and is right around this area where it's going to come back up. So the data rate therefore must be close to 3 gigabit per second, just above 3 gigabit per second. We can tell that by looking at just the shape of the spectrum. Now if it's went a little bit higher, we could tell exactly, but since the spectrum analyzer only goes up to 3 gigahertz, we can only estimate it. So, but I know that it's around 3 gigahertz. In fact, it's 3.125 gigabit per second, which is kind of a standard data rate for this type of transceivers. So we can start with that. So we have a PRBS sequence. We don't know what type of PRBS sequence it is. We don't know if it's a 2 to the 7, 2 to the 9, 2 to the 10, 2 to the 20. We don't know the length of the PRBS sequence, but there's a way to find out. Because the PRBS sequence is periodic, its spectrum in the frequency domain is going to be discrete. Now, when you look at this curve, you're going to ask me, well, this does not look discrete. This looks like a continuous spectrum. And the reason it looks continuous is because the tones are so close together that you cannot see them at this resolution bandwidth and looking at them from so far away. So, I hope you're not confused so far, but let's zoom into the spectrum and see if we can see the individual tones. So, I'm going to start this spectrum analyzer from let's start from 10 kilohertz. The reason I'm starting at 10 kilohertz is because this is rated to 9 kilohertz. So let's start at 10 kilohertz and let's stop at 11 kilohertz. So we're only looking at 1 kilohertz of signal. So far we don't really see anything meaningful. So let's reduce the resolution bandwidth and improve the sensitivity of the instrument. There it is, 10. That's the lowest resolution bandwidth we're going to be able to get from this instrument, and that's very important because without it you really wouldn't be able to do this. So let's do the other things we did before in order to reduce the noise. Let's change the reference level to minus let's say 30 dBm. There it is. Let's turn the attenuator to 0 dB to give us a little bit more signal to noise ratio, and let's turn the preamplifier on. There we go. So now I've done everything that I can to reduce the noise, and now you can see once the sweep is completed that there is in fact tone here, a tone here, a tone here. So the signal is not continuous. This line that you see at the bottom, that's the noise of the instrument itself. In reality, if the instrument was noise free, this line in between the two tones would be at minus infinity, so there would be no noise. These are the actual tones from the signal, so we can detect them. So let me put a peak search on this tone, and let me do a delta. So if I go under marker and I go delta right here, I can move a reference marker to the second tone. There it is, right there. And oops, well, that was my mistake. I pressed the wrong button. Let's do this again. Delta, move it again, and here it is, 373. So it's telling me that the two tones are 373 hertz apart. Now the distance between these two tones is also 373 hertz. These tones exist from DC all the way up to 3.125 gigahertz, but we're only looking at 3 of them right now, which are between 10 to 11 kilohertz. So I told you the PRBS sequence is periodic, and the distance between the two tones can tell us the length of the PRBS sequence. So let's do a quick calculation. So if I take some calculations here to find out what that 373 hertz tone spacing means in the number of bits. So let's take, we know that the sequence is at 3.125 gigabit per second, so 3.125 gigabit per second and it has a repetition rate of 373 Hertz. So which means the sequence is 8.3 million, there's an M here, so there's 8.3 million bits is the length of the sequence. Well, what is that in 2 to the power of something? So I want to find it in base 2, so I take the log 10 of the answer, and then I divide the whole answer by log 2 in order to find it in base 2. There it is. And it tells me 22.998, which is 23. So by measuring the spacing between the tones here, I have found out that the PRBS sequence is 2 to the 23. So this is a 2 to the 23 PRBS sequence that I found by measuring that. And we can verify that by looking at the computer, just so we can be convinced. If I can get my computer to start again. Here it is. The link is running, so I'm going to zoom in to the link parameters. There it is. It's refreshing. And oops, and this is it right there. You can see at the bottom, it actually pointed out. So right here it says PRBS 23. That's the length of the PRBS, and it's telling me that the data rate is 3.125 megabit per second, 3125, which is exactly what we thought. So by doing the measurement, remember, we didn't use an oscilloscope, we didn't use a pattern detector, we didn't capture the bits, which would have been quite difficult. We just looked at the spectrum. Because of the capabilities of the spectrum, we are able to find out that the sequence is 2 to the 23 and the rate is 3.125 gigabit per second. So next let's take a look at the demodulation capability of the Spectrum Analyzer. The Rigol Analyzer comes equipped with demodulation software for FM and AM modulation. So we're going to choose FM, but to make it more interesting, let's actually do a wireless transmission and demodulate it and listen to it, because it has a built-in speaker from the analyzer itself. To do a link, I've chosen to use these horn antennas. These horn antennas are very broadband. They work from 2 to 18 gigahertz. And you can see the internal structure of the horn antenna. It has these striped ground lines, and it has the shape of this metal in the middle. And if you look at deep in the center, there's a pin, and that pin is connected directly to the SMA connector, which does the coax to waveguide transformation, and from that the wave propagates out. This thing has about 8 dB of gain and is polarized because of the shape of the metallization that's inside it. So we're going to use it in this orientation like this. I'm going to connect it directly to the Spectrum Analyzer, and then as far as the carrier frequency, since this guy it works from 2 to 18 gigahertz, let's just choose 2.5 gigahertz, just above its lowest frequency where it is rated. So this is going to be a receiver. It's directly connected to the Spectrum Analyzer. And as for the transmitter, I'm going to use my Agilent E4432B signal generator, which has a capability to do FM, AM, and all kind of modulations automatically built into it. But instead of just transmitting a tone, I'm going to use its external input that's connected to these two cables, and it goes into this audio cable, and the audio cable is then connected to my iPad. So I'm going to use Pandora, transmit music audio signal from the cable. The audio signal will come into the external port of the synthesizer, and the synthesizer will then upconvert that to a carrier frequency that I'm going to choose. The output is going to come out of here. It's going to be connected to this second antenna, and this second antenna is going to transmit outwards, and then the signal is going to be received by this antenna, and then we're going to demodulate, and hopefully we should be able to listen to the music, transmit it, and then receive by the Spectrum Analyzer. So let's set this guy up for that purpose. So I said we're going to choose a carrier frequency of 2.5 gigahertz. There's our carrier frequency, and I'm going to put a lot of amplitude out so that it can have a strong signal, let's say 12 dBm. And I'm going to go to the FM modulation menu. I don't know if you can see that, but it has a whole bunch of paths that it can do a whole array of different type of modulation. So I'm going to say the FM deviation. Let's set the FM deviation to be around 20 kilohertz. That's how far from the carrier it will deviate the signal in terms of the frequency modulation. And I'm going to say the FM source is external, DC coupled. That's this guy. So now this guy right here. So the signal is going to come from here. It's going to use that as a signal to modulate and provide an output. So it's at 2.5 gigahertz. The modulation is now enabled, like so. There it is, FM1, is on, 20 kHz deviation, external DC coupled, and I'm going to now enable the modulation, and I'm going to enable the output. So now it's actually transmitting the FM modulated signal, and I'm going to turn the iPad on. There it is. So now it's transmitting music from, it's receiving the music from here, going in here, up converted, out of here, through the horn antenna, and I'm going to align the horn antenna to the receiver, and let me come here so I can get a reasonably strong signal. I'm aligning them. There it is. That's good. There we go. And there it is. So it really is the signal from the horn antenna. If I put my hand in front of the horn antenna, you can see the signal go down. If I remove my hand, the signal comes back up. So it's really coming from there. So now let's try and see what the signals look like in the frequency domain. You should have the music on top of it. It's a modulated, that is modulating the music. So let's go span. Actually, let's set the center at 2.5 gigahertz. Since we know where that music is, let's reduce the span to 100 kilohertz, like so. You can see it's kind of wiggling around. That's because this FM modulated and with the music on top of it. So let's clean it up a little bit. Let's reduce the resolution bandwidth to about 300 hertz. Let's change our span to to amplitude to -20, our reference. Turn the attenuation off, like so. And I don't think I did that. 0 dB, there it is. The reference level is at -20 dBm, and let's turn the preamplifier on to further reduce the noise of the signal. And I think I'm going to change the reference back. I'm not too happy with that. The reference -20 dBm. Oh, it doesn't allow you to do that once you turn the preamp on, because it doesn't expect you to receive a signal larger than that. There it is. So I'm going to take the peak. I'm going to put that to the center, and let's see if we can demodulate that. So I'm going to go to the demodulation menu. I'm going to enable demodulation. I'm going to say demodulation is an FM demodulated signal, and I will set the demodulation time to 60 seconds. That's 1 minute, and turn the speaker on. There it is. I got it. So you can listen. And now it's very quiet. Increase the volume a little bit. There it is. There, so you can listen, that's Queen of course playing. So you can see that what I've done is that the volume is at 80 and I'm demodulating 60 seconds worth of it, so I can reduce the volume. Like so. Now, there's noise in the background, of course, because that's the noise floor of the instrument. The link is not perfect, the SNR is not very good. But we have perfectly demodulated. We have up-converted our music from here using the synthesizer. We have a horn antenna that's transmitting the signal, and a horn antenna that is receiving the signal, and the demodulation functionality of Spectrum Analyzer, which we can listen to the music. So I can stop the music, I can pause it, start again, directly from the iPad, and you can see that it is a full length. Next, let's look at the tracking generator function of the Spectrum Analyzer. So the Spectrum Analyzer comes with a built-in generator inside it that covers the entire frequency span of the Spectrum Analyzer itself. So a tracking generator is an internal signal source that is locked to the sweep frequency of the Spectrum Analyzer itself. As you know, the Spectrum Analyzer only measures one frequency at a time, and it's just sweeping really fast across the screen here. You can see it refreshing. So if I had a signal source that was locked perfectly to the frequency that the Spectrum Analyzer was measuring, I could use that tracking generator in order to do measurements and turn the Spectrum Analyzer into a scalar frequency response measurement unit as well. It can measure the frequency response of both active and passive circuits, given that the tracking generator is of high quality. So let's try and run some of those experiments and see how well it behaves. You can enable the tracking generator in this unit by pressing the source, and you can see the tracking generator function up here. and you have a whole bunch of array of options. You can set the tracking level output power, which can in this instrument be from -20 dBm to 0 dBm, and you can do a power sweep, and the power sweep means that as the frequency increases, the instrument can actually change the power coming out of the tracking generator, and that's useful if you want to compensate for losses of cables or other passives that might be in the way. And you can also set a frequency offset, a small frequency offset inside there, and then you can normalize, which is very important. We will do that. By normalizing, then you cancel the effect of your cables and you de-embed them from your measurement. So in order to make a good measurement and good frequency response measurement, first we have to de-embed our cables, the effect of our cables, even though they don't really make so much of a difference to this frequency, but it's always good practice. So here's the tracking generator output, and here's the RF input, and I want to put my device in the middle in between these two. So first I need to cancel the effect of the cables themselves. So I'm going to use a through. I'm going to connect a through connector from here to here. Now I have a loop where the tracking generator output is directly connected to the RF input, like so, and then I can go ahead here and turn the tracking generator on. So the tracking generator is turned on, the output is at 0 dBm, there is no power sweep, so you can see it's measuring something at the top. It's not perfectly linear because the tracking generator output has to be de-embedded, so essentially for its own imperfections. You can see it has some dips and so on. So first thing what we can do is let's change the let's go ahead and normalize that. So I click on normalize and I will turn normalize on. There it is. So now you can see the line is perfectly at the top of the screen, so it's canceled any imperfections and the losses of the cable, and I can position the normalized reference a little bit lower. So I'm going to put it at 80%, so that it just puts it a little bit lower than the top of the screen, so you can easily see it a little bit better. So there it is. Now we have a perfectly normalized curve. You can see it's completely flat. Let me press escape, and if I put a marker on it, you can see it says 0, because this essentially there's nothing here, it's canceling all the losses. So if I remove the through now, you can see that it goes all the way down. So right now there is nothing connected, and we have -57 dBm in our current setting. So that means there's essentially a completely open in this case. So first let's measure this guy. This is a very simple step attenuator that's manual. You can see it goes by steps of 1 dB, and it goes all the way up to 11. This works from DC to 4 gigahertz, so it's perfect for this application, this test. So let's set it to 0, like so, and let's connect it and see if we can make an accurate measurement. It's a little bit difficult with the camera in the way. Here we go, connecting the input, and now I'm connecting the tracking generator, and there it is. There. So you can see it's connected like that. You can see the marker says -0.24 dB. So this attenuator, when it's set to 0, has about 0.25 dB of loss at 1.5 gigahertz. So now I'm going to step through the attenuation. So I'm going to go to 1. There it is. You see, -1.24, 2. Oh, this attenuator actually is partially broken. I did not realize. Let me see. Yeah, well, looks like it doesn't. There you go. See, that's a perfect example of using the instrument to find a fault. If you look here, this is not acceptable, because this tells me that at low frequencies this attenuator has 40 dB of loss, and at 20, you know, even if I move the marker, here, let's say at 500 megahertz, 450 megahertz, this attenuator has -7 dB of loss. It shouldn't. It should only have 2 dB of loss. So in fact, let me wiggle it. Oh, you see? If I by just tilting this a little bit, I managed to correct the problem. So there must be a contact issue inside this, which I did not know about. There we go. So we just found a fault in one of my components just by simply measuring it for this video. So anyhow, now it seems to be okay again. So 2 dB, it's broken again. Well, there you go. That's 3 dB, 4, 5. Okay, it doesn't work at 6. Doesn't work at 7 properly. 8, it's okay. 9 is okay. 10 doesn't work. And 11, is kind of okay. So anyhow, I have to repair that. So you can see 11 dB attenuation, and it says minus 11.55, so everything is looking good except for the fact that the attenuator is broken. So you can see quickly how easily I was able to find a fault with the attenuator, seeing the low frequency response by measuring its frequency, by measuring its complete frequency response. Let's do another quick example. Here I have a tunable bandpass filter that goes anywhere from 1 gigahertz all the way to 2 gigahertz. So it's a bandpass filter, so it only allows a narrow band of signal to pass through, and you can adjust that. It's mechanically pulls the filter around in order for you to be able to do that. So let's set it to 1.5 gigahertz like so, and let's measure its response to see if it is indeed what it's claiming to be. I think this is bidirectional, so I'm going to connect it this way and this way, and there it is. Let's see. So I'm setting it to 1.5, and let's look at the response. You see, perfect, exactly what it is supposed to be. Right now it's set to 1.5 gigahertz. If I do a peak search, there it is, 1.52. So it has a small band. It has a small band pass, so it works from 1 to 2 gigahertz. So let me go start the frequency at 1 gigahertz and stop the frequency at 2 gigahertz. Where's the stop? There it is. Okay, it's already doing that. So there, I can shift it around. Oh, you're not looking at the whole thing. There, I can shift it around, see? By turning the knob on the bandpass filter. So now by doing that, if I go back to, let's say I set it to exactly 1 gigahertz, you can see, you can characterize the frequency response, the performance of the filter by putting a marker on it. So for example, if I want to find the 3 dB bandwidth of the filter, I can do it very easily by changing the, I can change the start frequency, let's say at 500 megahertz. I can set the stop frequency at 1.5 mega, stop frequency at 1.5 gigahertz, and the start frequency at 0.5 gigahertz. So now if I place a marker in the middle, I can do a delta marker and find the 3 dB bandwidth by lowering until I read 3 dB. So it's very, very sharp. Approximately here, 2.5 dB. So it has only 21 megahertz from the center. So it has a very, very sharp roll-off, as to be expected for such a large structure, because you can make a very good filter if you don't care about the space that you're occupying. So perhaps something more interesting to measure would be an active amplifier as opposed to something passive. So here I have a mini circuit ZFL500LN, which is a low noise 500 megahertz low power amplifier. So I want to measure the gain of the circuit using the Spectrum Analyzer's tracking generator. So again, I've done exactly the same thing. I've enabled the tracking generator at minus 20 dBm this time, because whenever you're measuring an active circuit, always start at the lowest tracking generator level in order to not saturate the amplifier and also avoid potential damage to the amplifier or to your instrument itself. So I have minus 20 dBm, so let me normalize that. I'm normalizing this again. So by normalizing it, it actually takes the minus 20 dBm and puts it at 0 dBm. So don't get confused when you see 0. This is gain. This is not the output power anymore. This is relative. So relative to the minus 20 dBm, we have 0, which we should, because we are measuring just the through right now. So I've done my calibration. So I will now remove once again the connector, no problem. And I will connect now the instrument directly to the amplifier. So now this is important. So the input goes on this side. Now the amplifier is turned off right now. You should never apply a signal with the output of the amplifier open like that if you're not terminating it, because you could damage the amplifier. There it is. So I'm going to let it just hang out here, and I am measuring this waveform. So now, why is this important? Because this is the isolation of the amplifier when there is no power to the amplifier itself. So if I put a marker you can see that 1.5 gigahertz, the amplifier has only minus 23 dB of isolation. So it still allows the signal to go through, but only by attenuating it by minus 23 dBm. But you can see this shape here. This is very common because the parasitics of the device begin to become more and more dominant at higher frequencies, so the isolation of the device gets worse and worse when it's turned off. So if I go all the way to the end, you can see at 3 gigahertz, the amplifier's isolation is only minus 15 dBm, minus 15 dB. So let me put the marker back at 1.5 gigahertz, and I'm going to now apply the power. So I have, let me get the camera, here we go. I'm using the Rigol DP1116A amplifier. This is a 15 volt amplifier, so I'm going to put it into 16 volt mode, put 15 volts like so, nice and easy, and I'm going to enable the output. There it is. So the amplifier is currently consuming 0.8 watts and it's taking 54 milliamps, so it's now turned on. There we go. You can see the amplifier now the response has changed significantly, and we can see that the response is outside the display. So let me go ahead and change the reference level to 20 dBm, like so. So we can see better what we're doing. And I'm going to go to the source and I'm going to change this to, let's say, 50%. There we go. So it's one of the annoying things about the way that this instrument handles where you reference it. So if you have enabled the tracking generator and then you change the reference, it doesn't move the curve down for you. You have to go down to the normalize menu and then move it. They've done that so that you don't accidentally forget that this is a relative measurement. But anyhow, just keep that in mind. There it is. So it's telling us that the amplifier, remember, this is my reference. This is 0 dB of gain right here, this thicker gray line, which is nice, it shows that. And this is the gain of the amplifier. And I can move the curve, I can move the marker down here. There it is. So it's telling me that this amplifier, let's go to 100 megahertz, which is right there in this region of operation, has 27.98 dB of gain. So about 28 dB, which is exactly what its datasheet says. It says its typical value is about 27 or 28 dB of gain. And you can see that up to 500 megahertz, if I put this to 500 megahertz, it performs brilliantly. It's almost completely flat, its response, which is exactly what you would want. And after 500 megahertz, it still has gain, but it rapidly starts to drop. And this is, again, normal because it's only rated up to 500 megahertz. But because we can measure up to 3 gigahertz, we can see that exactly the curvature of the instrument. Now, there is something else you can do. If you want to find out what is the maximum power this circuit can put out, well, let's think about what we're doing. We are putting into the instrument minus 20 dBm. So if I go to the source, the tracking generator is putting minus 20 dBm. And if it has 27.68 dB of gain, it is putting out right now 7.6 dBm of output power. And if I were to increase the tracking generator level, eventually the amplifier will saturate. And the output will no longer go higher, see? The difference between 0 and 1 and 3, it doesn't move down anymore. That's because I've saturated the amplifier. So by using the output power control of the tracking generator, you can actually measure the saturated output power of the circuit. So if I go up by 1, 2, that went up by 2, there you go. So it's around here or so. So it cannot put in more than that. So its saturated output power is about 10 dBm, which is exactly what the datasheet also says. So you can use, by adjusting the output, by adjusting the tracking generator's level, you can actually measure the compression point. You can also do a power range where you slowly slope the power to measure it, but anyhow, this video is getting already way too long. So you can also do that. Just keep in mind that you can use that functionality for that purpose as well. So let's look at another very important experiment. If you have a tracking generator like this one, you don't have to just, you can measure more than just the gain through the circuit. You can also measure the return loss or the voltage standing wave ratio of the device you're testing. So for example, let's consider the amplifier that we were using. This amplifier receives power from this port and outputs power from that port. But not all the power that you put into the amplifier gets into the amplifier itself, because some of the power gets reflected back due to impedance mismatches at the input of the amplifier than the impedance at the output of the tracking generator. Normally, you would want all of the power to go in. So if the output of the generator is 50 ohms in this case, which is for most instruments, if this is 50 ohms, then you want this to also be a perfect 50 ohms, so all your power goes in and none of it gets reflected. The reflected power is essentially wasted and can cause some other problems. In order to maximize your signal to noise ratio, you want to pass all the power that way. So when you design an amplifier or a passive, you want to know how well it's behaving. You don't just measure the waveform going through this way to gain of the amplifier, you also want to find the return loss. Or for example, in the case of this filter, which is what we're going to do for the experiment, I found out the response for the signal going in and then coming out, but I want to know what the input impedance is and how well the signal is absorbed into the instrument itself. Now with a tracking generator like this one, with a spectrum analyzer, you cannot do a vector measurement. So you cannot know the phase of the signal, but you can know an absolute magnitude and absolute amplitude of it. So you can find the magnitude of S11 and S22 in the S parameter domain, or you can find out exactly the voltage to standing wave ratio by doing that. So in order to do that measurement, it's not so straightforward as just putting it through and calibrating. You have to do a more sophisticated calibration to be able to do that. So we're going to use a Hewlett-Packard 850560, which is a very common calibration kit. This one is a 2.4mm calibration kit, so it works all the way up to 40 GHz, which is an overkill for our experiment, but that's the only one that I have available here. So if you look inside, it essentially comes with a standard of impedances that you can use. It also comes with this awesome tape drive kit that has all the calibration standards in it that would be read by some ancient instrument that's no longer available. But the standards don't change. The laws of physics haven't changed yet. So this is an open. So this essentially is an infinite ohm, ideally, all the way up to 40 gigahertz. So that's why this is that you cannot just leave the port open, because if you just leave it open, it will not be like an actual open at RF. Or here, let me see, there's a short, here we go. So this is a short, so this would be 0 ohms all the way up to 40 gigahertz, exactly 0 ohms. So we can use this one, and we also need an actual 50 ohm, something that's calibrated to be perfectly 50 ohm, and that is this guy right here. Let me say that right there. It says, I don't know if this is going to focus on that, but it says 50 ohm, and it will work all the way up to 40 gigahertz as well. So there you go. Now these are K-type or 2.4mm type connectors. They are not compatible with SMA. This is an SMA, which has a Teflon core. This is a 2.4mm air around it. The dielectric is air. These are not compatible. If I connect these together, I will destroy this. So you need something that converts from a K to, I'm sorry, this is from a 2.4mm, not a K, from a 2.4mm to an SMA. So here I have a converter. This one is actually a V connector. This goes up to 67 gigahertz, and on the other side is a K connector, which is SMA compatible, and this is 2.4mm. 2.4mm and V are compatible, so I can screw these together like so, and they fit perfectly, and then the other end fits into the SMA. There you go. So this is very common anyhow. Just wanted to let you know, don't make that mistake. You will destroy connectors. These are extremely expensive. Alright, so let's do that. But just having the standard isn't enough. We need something else. We need something to be able to extract the reflected wave. And for that, we're going to use a directional coupler. So the way this guy works is that if I put a signal in here, it travels all the way forward and comes out of that end. But if I put in a signal this way, it doesn't come back this way, it goes back out that way. So you can see why this would be perfect for what we want to do. If I have a device, if I have my amplifier here, connected to this end, like so, and the signal will come through here, will hit my amplifier, on its way back, it will bounce back and come out that way. That's how directional coupler works. So if I were to connect my tracking generator output to here, like so, if I can do that, there we go. Now I can connect the device that I want to measure the voltage to standing wave ratio here, and I want to measure the reflected wave that's coming out that way, so that I'm going to connect my spectrum analyzer to the couple port as opposed to the output port. So this is a through port, this is a couple port, so I'm going to connect it to the through port. So the signal comes from the tracking generator, goes this way, bounces against the device I'm testing, comes back and goes that way. But I need to calibrate the instrument so that it knows what an open is, so it knows what is the absolute maximum reflected wave it can possibly measure, and that way I will de-embed the losses of the coupler as well as the cables. So what I'm going to do in order to do that, I am going to take my short. So this is a short, as I mentioned. Yes, this is the short one. So if any wave that has an impedance of 50 ohm hits this, all of it reflects back because of the transformation because of the impedance mismatch. So this is a perfect reflector of wave for me across all frequencies. So I'm going to take this guy out, and actually let me get one that has the right connector. That's an open, that's an open. There we go. I wanted a short that had a male connector. The other short that I was using had a female connector. So they're both the same, except the connector is different. So here we go. I'm going to connect, again, this is a 2.4 millimeter connector. You've got to be very careful. Connect it to this guy. Now it's SMA compatible, and I'm going to connect it directly to here. So what I have built is a perfect reflector. All the wave that travels through here hits the short, completely mismatched, all of it bounces back, comes back this way. Now I can calibrate the instrument, which is now in screensaver mode. There we go. So go to the source, tracking generator. I'm going to turn the tracking generator on, and you can see it is measuring -20. That's the loss of the coupler. So the coupler has 20 dB directional coupling loss this way. So now I'm going to tell the instrument to normalize this waveform. So I'm going to say normalize, and I'm going to turn the normalization off, and it puts it back all the way up to 0, and I'm going to bring it down to 80% like last time so we can see it a little bit better. So this tells me that, so when it says 0, it means all the wave is reflected. So if I remove this from here, there we go, that's an open. So you can see this is the response of an open, and not an actual open, but an open that's missing something. So now if I terminate it with a 50 ohm, none of the wave should reflect back. So I can verify my calibration by connecting a 50 ohm here, and this 50 ohm will absorb all the signal, so then I should see this wave completely drop because everything is being absorbed. Here we go, try that. There it is. You can see, perfect. So it's absorbing all of the signal. This is because it's a very good 50 ohm. Now I'm ready to connect the output to my circuit and actually see the exact value of my filter's voltage standing wave ratio. There we go. So here's the filter right here. So I'm going to, let me see if I can do this properly. There it is. I need one more SMA cable. So let me explain this circuit again. So here is the RF input coming out through the coupler, goes out here, goes into the filter. Whatever impedance mismatch is here causes the signal to reflect back, comes back through the green cable, goes down here and goes up there. Now, when I calibrated this, I calibrated at the end of this cable, but I'm measuring this also. So keep that in mind, because my calibration isn't precisely valid because of this cable being in the way. So this is a good example for you to keep in mind. My calibration plane is at this point, but I've added this cable. So in reality, I should have added the open or the short in here, done the normalization, and then the measurement. So it's going to cause some inaccuracies, but it's going to get the message across anyway. And here's the result. You can see that the filter reflects all the wave except for where it's tuned at, which makes sense because that's the band pass behavior. So if I zoom in around that area, Let's change the span a little bit. There we go. So I lose the calibration when I do that, but anyhow, but you can see that it has a 20 dB of less return at precisely the frequency where it's tuned at. So I can change the tuning frequency. You can see that the return loss changes. So right at that point, we already measured its response, its gain essentially. It went like this. So right at that point is where it passes a signal, and right at that point is where it absorbs the signal. So it makes perfect sense. So by using the tracking generator and a directional coupler, which Rigol sells their own directional coupler. This is an HP one that I had. I don't have that particular one that they have, but you can see you can use this one to measure input return loss. So as one final thing I wanted to show you is the ability to use zero span on the spectrum analyzer. Now, all spectrum analyzers have a mode called zero span, which means that the frequency span of the instrument is reduced to zero, like it's shown here. So let me preset this so we can see from the beginning. So right now it's spanning from 0 to 3 gigahertz. I can set it to span at exactly a single frequency and nothing else. So I can put it to zero span. Right now it's on zero span, and its span is only at 1.5 gigahertz, like so. So it's now from here to here is now in time, not in frequency. This is a span of time, which is 100 milliseconds. So now, why is this good? Well, aside from the fact that you can do AM demodulation and all that stuff, if you have a tracking generator in your spectrum analyzer like this one, by setting it to zero span, you've gotten yourself now a synthesizer, because by enabling the tracking generator, you now have a tracking generator that outputs exactly a single frequency and nothing else. So it's not sweeping anymore. So now, not only you've bought yourself a spectrum analyzer, but you've also bought yourself a synthesizer that can go from 9 kilohertz to 3 gigahertz. So let's take a look at the quality of the signal that's coming out of the generator output and see if it's suitable for use as a synthesizer. So I'm going to, right now it's at 1.5 gigahertz, I'm going to go to source, and I'm going to enable the tracking generator at its highest amplitude, which is 0 dBm. And what I've done is that I have connected the output of the tracking generator to my other spectrum analyzer across the lab, here, like so. And you can see that it is generating a 1.5 gigahertz signal with some other minor tones around it and a second harmonic of the signal. So the signal coming out of the tracking generator is okay. It's not very good, but it's reasonable. You could still use it as a synthesizer, in some situations. Now it could be better. Let me, for example, try reducing the amplitude. This is minus 10 dBm, so it's a lot more clean than minus 10 dBm, and here's minus 20 dBm. So you can see that the harmonics are smaller. So, but usually you would want to be able to use it at 0 dBm, and you can see it has a strong second harmonic. So let's try some other frequencies also. Let's say the center frequency, instead of 1.5 gigahertz, let's try 500 megahertz. There you go. So you can see all the other harmonics there. It's okay. It has a total harmonic distortion of about maybe 22, 23 dB, which is not very good, but it's still usable for some applications. But you have to keep that in mind, that it is generating strong harmonics. What about higher frequencies? 2 gigahertz? So now you can see that the tones are surrounding the signal themselves. It's because of the way it generates these signals, so that the harmonics are now close to the intermodulation products are present near the fundamental frequency. Let's try 3 gigahertz, which is the highest frequency. Now at 3 gigahertz, it is producing signals that are below 3 gigahertz, and I cannot see the harmonics anyway, but you can see that it again has a total harmonic distortion of this time maybe even less than 20 dB. So you have to be careful, keep that in mind, that even though it is a tracking generator inside it, its quality of the output is not very, very good. Might be usable for some cases, but maybe not so much for broadband applications. The DSA1030A has a lot of other functionalities built into it, which I haven't gone through, otherwise the video would be longer than it is now. For example, it has a whole array of measurement capabilities which you can access through the measure button and you can measure total power, channel power, bandwidth, all kind of a whole bunch of advanced measurements that are built into it, like a harmonic distortion, or you can even create a mask which will give you a pass or fail. So if you're doing some kind of an FCC regulation, you want to make sure you don't occupy a certain bandwidth, you can use all these built-in functions. So there's a lot of very sophisticated measurement functions which I will try and cover in a different video, a different tutorial maybe that's more related to these total type of measurements. And of course, just like any other spectrum analyzer, it can grab data, plot it. It has multiple traces. For example, it has several traces which you can enable on the screen at the same time, so you can do relative measurements. You can hold and freeze a trace on the screen and then read it back again. And again, you've already seen it do the probe. I've used the probe functionality in a different video. So overall, I've been using this for quite some time, and I've gone through several firmware iterations, and there's a few other things that I've asked Rigol to correct, and they're working on that. So overall, I'm very happy with it. Some of the things I didn't like I mentioned throughout the video, and I was hoping maybe the tracking generator would be a little bit more clean. Sometimes some of the functionalities are a little bit difficult to get to, but overall I think it's a very, very good bang for the buck, as are all Rigol instruments, is that you're getting a lot for very little money, and the performance is very good for what you're getting. So again, I recommend the DSA1030A, or if you want to save yourself some money, look at their 800 megahertz and 1.5 gigahertz options. Those are really, really good buy. I have played with both of those before, and I am using one of them somewhere else, the 1.5 gigahertz option. Very, very good instrument as well. This is their top of the line. If you need very low noise, if you need advanced measurement functions, and if you like to have the lowest resolution bandwidth and a built-in preamplifier, this is the unit for you to get. And please, if you've reached this part of the video, thank you, and please leave a comment, discuss this, rate the video, and if you happen to get something like this from Rigol, let them know that you have watched this review. Alright, until next time.